next speaker and the last of this morning, first session in the morning is Melanie Kaasinen from working at ESO. And Melanie is going to talk about resolving cold gas at cosmic noon. Please.
Can you see the screen?
Yes. Can you switch to the presentation mode?
Is it not? Yep. Hang on a second. Okay, is that working now?
Yes, thank you. Perfect.
Awesome, thank you. All right, so hi everyone. I'm Melanie Kaasinen. I'm a postdoctoral fellow at ESO. And I just want to start by thanking the organizers for a really interesting and diverse science program. So I've been learning a lot. So I'm going to present a slightly different kind of talk in that I'll be focusing mostly actually on the limitations of existing ALMA observations of cold gas at cosmic noon. So why should you care about cosmic noon? To answer that, I'm starting with a plot showing you the cosmic star formation rate density, so averaged over the entire moving cosmic volume, as a function of redshift. So early on in the universe, the star formation rate density increased, peaked around redshift 2, and it's since declined by more than an order of magnitude. Now, integrating this plot tells us something really interesting about our universe, and that about half of the stars in the local universe were created in this really narrow redshift window around redshift 2. So to understand how stellar mass was assembled so rapidly at this epoch, it's really important that we look to the sites of star formation. So where did the stars form and under what conditions? So stars form predominantly from molecular hydrogen, and unfortunately, though molecular hydrogen is not visible in emission at the cold temperatures characteristic of star-forming gas. So instead, we've come to rely on other trace components. So for local galaxies, it's very common to use observations of the ground transition of carbon monoxide, and in fact, a lot of calibrations on this are based on this. But at redshift 2, CO1 to 0 is shifted out of the wavelength range that's covered by ALMA. So for redshift 2, if we want to observe CO1 to 0, we have to use a very large array, and it takes many hours of integration time even to perform unresolved observations of really bright galaxies. So instead, the community has come to rely on submillimeter observations of other traces. So one common way of measuring the global molecular gas content of these high redshift galaxies is to use single band dust continuum observations taken with ALMA. So dust continuum has been calibrated against CO1 to 0, mainly using local galaxies. And a couple of years ago, we tested this calibration and showed that it is robust for massive star-forming galaxies at redshift 2. So the other main way to study molecular gas at high redshift is to use higher rotation CO transitions. So particularly at redshift 2, the CO3 to 2 transition. So this first has to be corrected again for the state of excitation of the gas down to CO1 to 0 in order to infer the molecular gas content. Okay, so studies based on dust and CO emission have been conducted over the last decade with ALMA. And here I'm going to highlight some of the results. So here I'm showing you the molecular gas to stellar mass ratio as a function of redshift. And you can see there's a big difference between galaxies at redshift 2 and in the local universe. So galaxies around redshift 2 have about the same amount of mass in molecular gas as they do in stars, whereas local galaxies have about 1/10 of the mass in molecular gas compared to stars. So this big difference in the gas fractions also implies that there must be a fundamental difference in the structure of galaxies at redshift 2 compared to redshift 0. And that's, of course, the gas is just far denser at redshift 2. Okay, so for local galaxies, ALMA is really now providing us these very detailed maps of molecular gas. So here I'm showing one example from the FANGS ALMA survey of the local spiral galaxy. And with the FANGS data, we're now looking at molecular gas at scales of less than 100 parsecs. So this is revealing, if you look at the orange, CO2 to 1, the sites of star formation. So you can see that star formation is occurring in spiral structures and bars. People are measuring the time scale for star formation and testing star formation theories. And for more on that, I really encourage you to go to Jai Soom's talk tomorrow. So another thing it's being measured with these really high resolution CO observations is the thickness of these gas disks. So gas appears to have settled into quite thin disks by redshift 0 of velocity dispersions of around 10 kilometers a second. So how does this compare to the distribution of molecular gas at redshift 2? Well, resolving cold gas at high redshift was actually one of the key science goals for ALMA. So let's take a look at whether or not this has been achieved. So some of the first studies of resolved dust and CO emission were really focused on looking at very dust-rich, highly star-forming galaxies, so sub-millimeter bright galaxies. So here's an example of some of this early work. Here you can see in the black contours, very compact dust emission, and you can see this compared to the CO emission in the orange contours. So what these first studies were finding is mainly that the CO emission appeared, the dust emission appeared more compact than the stellar emission. And in the very few cases where there was also CO emission, it also appeared more compact than that. But the thing I really want to highlight here is that despite the really good analysis of all these authors, these observations leave a lot to be desired. So the CO resolution is quite low, and also the sensitivity is still quite poor. So we really want to move on to studying more typical galaxies and also looking at high resolution and sensitivity CO observations. So with this in mind, we targeted the 3 most extended galaxies in the Hubble Ultra Deep Field, which already had CO detections from an ALMA large program. Actually, one of them is roughly up here. So here I'm showing you some of the highest resolution maps of CO emission and also dust emission at this redshift. And for more recent results, I encourage you to go to the very last talk of this conference. So just want to talk a little bit more about these CO observations. So for these 3 galaxies here, the data that I'm showing is made up of about 20 hours of the ALMA time. So that's 5 hours from the aspects program, an ALMA large program, plus 15 hours of follow-up targeted observations in a more extended configuration. And still we're at a resolution of about 6 kiloparsec. So what can you do with that kind of resolution? Well, you can study the overall extent of the emission from stars, dust, and molecular gas. And so in this work, we quantified that in various ways, basically by measuring the half-light radii. So one of the findings was that the dust and CO emission are more compact than the stellar emissions. This implies potentially large reservoirs of dust and gas that are centrally concentrated. But we also again found, like for the sub-millimeter galaxies, that the dust emission is more compact than the CO, at least for 2 of these galaxies. So this implies that dust is a poor tracer of molecular gas at large radii. And indeed, some very recent simulation-based studies are really showing that the dust emission is very sensitive to the heating by star formation, and so it's tracing high central star formation. Okay, one more thing I want to point out about these observations is what column densities they're actually sensitive to. So both our CO observations and others at this redshift are really only sensitive to the very high column densities typical of the central regions of local nuclear starbursts. So with these observations, we can't actually pick up the spiral arms of typical local galaxies, for example. So this may be why you don't see this feature that's in the stellar emission here in this little galaxy. Okay, so based on that, I would argue that we really still need higher resolution and sensitivity observations of CO emission in order to constrain the morphology of molecular gas. So in essence, what I'm saying is we'd like to go from blobs to galaxies, and to show you that this is feasible, again, I've taken a galaxy from the FANGS data set. So these are the CO2:1 observations. Now I'm going to assume that this galaxy has the same high gas fraction as a galaxy at redshift 1.5, which by the way, it definitely doesn't, and make some mock observations based on the existing resolution data at this redshift. So this is what we would have observed with current setups. If we now spend another 20 hours in a more extended configuration, then we can start to resolve the structure of this kind of galaxy. Okay, but so far I've been talking only about 2 dimensions, and I'd like to move on to 3 dimensions because there's a lot more fundamental science cases there as well. So actually yesterday, Fernanda presented some really interesting results and also the background science motivation. So I just want to highlight that measuring the gas kinematics is really important in order to study when galaxies settle into thin disks. So measuring the random motions of velocity dispersion really tells you about the competing effects of gravity and turbulence and the disk structure. So with the CO observations that we had in 2020, we fit a thin disk model, and this seemed to be a pretty good fit. So on the right-hand column now, I'm showing you the residuals. So with this, we could measure the maximum rotation velocity, but given the resolution of the data, we could basically only place an upper limit on the velocity dispersion. So even with that, we can start to say something about the rotation versus random motions. So here I'm showing you on the y-axis, rotation versus random motions as a function of redshift. And I'm really just focusing here on this key epoch around redshift 2. So the comparison samples that I'm showing you, these are all samples with observations based on ionized gas, so mainly H alpha. And there was also some discussion yesterday about whether these are really giving the same results as cold gas. So there's some indication that ionized gas studies are biased to higher values of velocity dispersion because of more energetic events. So it's very difficult still to compare these values. So nonetheless, we seem to find that these three galaxies are quite rotation dominated. And just to put this in context with some of the very recent work that's been done at even higher redshift with C2 emission with ALMA. So these are studies looking at very massive dust-rich, also lensed galaxies. They're finding very rotation-dominated systems. So it would be really good to start filling in this intermediate redshift, looking at cold gas in particular, and linking these two regimes also, again, to local galaxies. And for more on that, I also encourage you to go to Madeleine's talk. 3 minutes. Okay, so just to highlight why resolution really matters for these studies. So here I'm showing an example of exponential disk galaxies with a maximum rotation velocity of 300 kilometers a second. This is a model. There are two models here, one with a velocity dispersion of 80 kilometers a second, one with 20. And in the top row, I'm showing you the velocity dispersion maps at existing resolution. And in the bottom, I'm showing what happens if we go to much higher resolution, so sub-kiloparsec scales. If I now show you the profile of the velocity dispersions as a function of radius, you can see very clearly that with the existing observations, we can't actually distinguish between 80 and 20 kilometers a second. Whereas if we start going to higher resolution, we can actually distinguish between thin and thick gas disks. Okay, there's one more science case that I want to briefly talk about, and that is that we also really want to understand the physical conditions within the molecular gas. So by that, I mean both across, or in the resolved sense in galaxies at redshift 2 and also compared to local galaxies. So with physical conditions, I mean, how does the gas temperature and density vary? Now for local galaxies, you can look at dense gas traces like HCN. That's not possible at high redshift. So our best bet really is to use multiple transitions of CO plus dust continuum and ideally also atomic carbon emission. So if you start to have multiple transitions here, you can break the degeneracy also between the gas temperature and the density. Unfortunately, though, resolving all of these transitions for large samples of galaxies at redshift 2 is just not feasible time-wise. And so there's still two main options that we have at the moment. One is to probe the integrated temperature and density for samples of galaxies, so based on unresolved observations, and there's a few groups doing this. And the other option is just to look at a subset of lines for very few galaxies. So just to highlight that the second option can still be quite informative, here I'm showing you an example of a local infrared luminous galaxy. You can see very clearly that the CO6-5 emission is much more centrally concentrated than the lower J CO emission. And in this case, this is because the CO6-5 emission is very sensitive to the warm gas component. And the gas in this galaxy is clearly being heated by very high central star formation rates. Okay, so in the last 2 years, there's been some attempts to do this also with ALMA at higher redshift. So here's one example that I could really find, which is a nice map showing you a dusty lens galaxy, redshift 3. You can see two CO transitions here. So in this study, they also looked at the dust continuum and C2 emission, and they were able to measure some average properties of ISM conditions, but really the sensitivity here of the CO is not sufficient to map differences in temperature and density. And there's nothing like this around Redshift 2 either. So what I really want you to take away from this talk today is that I think we still need to resolve cold gas at cosmic noon in order to answer what were the main sites of star formation at this epoch, how star-forming gas is distributed relative to stars, so how thick are these gas disks, and what's the temperature and density of the star-forming gas. And so with that, I'm quite happy to take your questions now or any comments you might have.
So Melanie, thank you very much for the nice talk. It's very nice to show that we always should keep in mind what we are looking at. So the ALMA is maybe a very wonderful instrument, but when we are looking at those distant galaxies, it's still a very difficult job to do. So thank you for showing all this. We already have questions in the chat, I see.
Yes, we have a question. Is it possible to see outflows as a part of non-rotation motion in your analysis?
No. I mean, let's just say the data that we had was very well fit by a rotating thin disk. There was no evidence in the PV diagrams or anywhere else that there would be outflows. Also, whatever method you want to analyze this, also moment one maps, these galaxies really don't seem to have any outflows. But I think, yeah, even for that, it would be nice to have a bit higher resolution.
Of course, yeah. There's another question. Are there any resolved unlensed studies for the cold gas at high redshift?
Yeah, I mean, what do they mean by high redshift? I mean, this is basically these studies. Mm-hmm. So there's a handful of studies of CO of submillimeter galaxies, plus the study that we conducted. At even higher redshift for CO emission, it's mostly lensed. Yeah, there's a couple of VLA-based studies as well, but they're, yeah.
And there's one more question. Can we find a sample of strong lens galaxies around redshift 2 to improve the spatial resolution?
Yes, I think we can. Happy to talk to whoever asked that question. Yeah. I mean, the only difficulty with that, I guess, and again, I'm not an expert in the lens modeling, but there's been a lot of improvements on this. If you want to resolve multiple transitions and then actually compare the star formation rate surface density and the molecular gas surface density with lens galaxies, then that's a bit tricky because of differential lensing. So I think for that, you want an image that's probably not too distorted.
If I have a question regarding this. I don't know whether you have seen this in your data set, but something like an offset CO emission compared to the optical image or something misaligned, if you have seen something like that?
For these three, no, there's definitely quite a few examples where this is happening at high redshift. Quite often it's for these very compact galaxies as well. So because we basically already selected extended galaxies, which are likely to be extended disks, that wasn't the case for these three.
All right. There's another question or more comment. Avison et al. 2020 point out the possible clumps for high redshift strong lens galaxies might be just the dirty images we have.
Yes, and this is exactly my point to getting to higher resolution and sensitivity, because I think there's a few studies now that have shown that you can easily think that you're seeing clumps when all you're looking at is essentially poor signal to noise. And so I've actually, with my collaborators, done a fair bit of work on sort of modeling or simulating ALMA data. And yeah, we're finding the same thing. So yeah, that was a good thing to point out.
I think those are all the questions that we have.
Okay.
Thank you so much.
Okay, thank you very much, Melanie, for this talk. And again, thank you to all the speakers of this morning.